So describing sets of numbers, particularly solution sets, can be a tricky thing. And two different forms of notation have been devised for different situations that make the job much easier to do in a short, quick, and concise manner. So let's look at a few of them. One you already know, interval notation. You have worked with in the past if you had me in Algebra 2. It reports, for example, if I have a parabola and I want to describe the domain and range of this parabola, we know that the parabola goes and exists from negative infinity to positive infinity on the domain. The input values are not restricted in any way. And so we developed the notation for the domain equals all the values from negative infinity all the way to infinity. And of course we use a paren because infinity isn't a value. It can't ever be achieved. And so we have to use a parenthesis rather than a bracket. Infinity is not included in the set. So this would tell us the domain, what happens along the x-axis or x values we can choose. But the range in this case has a different set. The range values down here below 0, none of the y or output values exist below 0 for this function. So the lowest or the first output value that exists, let's call this 1, is at 1. And 1 is included. We're going to say that this the y-intercept for this graph is at 1. So we use a bracket to show that 1 is included. And then we show that all y values, integers, rationals, irrationals, all real y values that exist on that number line above 1 are included in the interval all the way up to infinity. So this is called interval notation because notice that the curve is continuous. It never breaks. There's no jumping around. It's a continuous set of values. And so interval notation works really well in this case, but it doesn't work in every case. But before we look at other situations, let's do a couple of problems to demonstrate situations where interval notation is perfectly suited. Let's look at describing values from between -2, less than and equal to, and +12, less than and equal to. So if I were to put this on a number line, it would look like this. I would have it's equal, right? So I would use a solid dot at -2 and a solid dot at 12 because I'm looking at equals, and then all the values, x is all the values in between because x values are bigger than -2 and less than 12. So interval notation for this is perfectly suited. Bracket because -2 is included all the way, every single value along the way until you get to 12, and 12 is also included. So you would have a bracket. Interval notation is beautiful there. B, we want to look at only values x greater than 4, x greater than -4. So a number line real quick just to get a picture of it. At -4, x values are greater than -4 and they don't include -4, so we use an open circle or an open dot, and then all the values up to infinity beyond -4. So interval notation here works well again. -4 is not included, so I use a paren, and then all the values in between up to infinity, and infinity is obviously not included. So interval notation works great there too. Sometimes we have a situation where we're looking at more than one part, a broken part on the interval, or broken intervals on the number line. So x less than 3, or x is greater than or equal to 54. All right, so let's put our number line together. So we're looking at 3 being a point of transition, right? One side, x values exist on one side but not the other. So at positive 3, and I'm going to put it over here because I'm noticing 54 is a big number and so we need room. So x equals positive 3 not included, x equals 54 included, but x values are less than 3 on this side and greater than or equal to 54. So there's a break right here in the middle. But this portion is an interval. From negative infinity to 3 is certainly a continuous interval, and from 54 to infinity is certainly a continuous interval. So we can use another sort of notation. It's still interval notation, but it has a little addition to it. We can say the interval from negative infinity to 3 not included, and the interval from 54 to infinity not included, obviously 54 included. And because this says it's either the left-hand side or the right-hand side, the symbol for that is sort of a wide U, means union. Right? So in set notation, this means union, and union means or. Another notation that you might have seen is this, which is called intersection, and intersection means and. I'm going to erase that because it doesn't fit here. So now let's look at another type of notation for reporting sets or intervals of values. Now this is called set builder notation. Set builder notation can be used in place of interval notation. It's a little more complicated, so if you don't need it, often we won't use it. But let's look at how it's set up. It also is more expansive. It can describe other sorts of sets. So let's use the same value or the same graph. Let's call this 1. So if I wanted to create set builder notation, first set builder has brackets on both ends, and I'll close this bracket when I'm ready. And you have to describe what you're looking at. So in this case, if I were looking at the domain, I know that I'm looking at x values. So I open the bracket and I say I'm going to talk about x values such that, that's what that line means. So this is the set, which is what a bracket means, of x values such that, and in this case I would say x is just included in the set of real numbers. Since it's everything from negative infinity to infinity, I can just say it's everything, right? So x is in the set of real numbers. And then close the bracket, and I finished that set builder notation for that domain. Now the range is going to be a little bit different here. I'm going to open the bracket for the range, and remember the range is the y values that start at and include 1 and complete at infinity. Well, I guess it never completes since it goes on to infinity. So I'm talking about y values such that y is greater than or equal to 1, right? Because I'm just saying it's all the y values bigger than or equal to 1, but I have to say which set, actually number set, is included in, or the set is included in. So I'm going to say such that, and y is in the set of real numbers. Okay, I put that together kind of funny, so let me say it again. This says the range is all the values, or the range equals the set of y values such that y is greater than or equal to 1 and y is an element in the real numbers. This little symbol, just like this symbol is part of set notation, so is this. This means an element in. Right. So y is an element of the real numbers. So let's use the same values we used before, only this time I'm going to use set builder notation. So for a, I would say that x is, or we don't know if this is a domain or a range, so I'm just going to say that we're talking about the set of x values such that x, I can just say this, negative 2 is less than or equal to x, which is less than or equal to 12, and x is an element of the real numbers. So I've just said in set value or in set notation exactly the same thing I said in interval notation above. So let's look at number 3, or C, excuse me. C would be the set of x values such that x is less than 3 or x is greater than or equal to 54 and x is an element of, okay, it's certainly true that x is an element of the real numbers because all of the values from negative infinity to 3 are real and all the values from 54 to positive infinity are real. So I would identify x is an element of the real numbers. But the beauty of set builder notation is that it lets you be more precise in cases that are more restricted. So for example, let's go ahead and call this D. So if I were looking to report or to describe a set of numbers 2, 3, 4, 5, 6, and 7, if I wanted to describe this in interval notation, I wouldn't be able to do it because there's nothing about interval notation. I guess I could say the interval 2, exactly 2, exactly 3, exactly 4, but that'd be crazy. Who would want to do that? That's just too much work. But with set builder notation, I can say that I'm looking at the set of numbers of x such that x is, 2 is less than or equal to x, which is less than or equal to 7. Now so far I'm just looking like interval notation. I'm saying everything, even 2.5 and 2 3/4 and 3.5 and 4 1/4 and all of the in-between values. But I can limit this. Notice these are counting numbers, 2, 3, 4, 5, 6, 7, or natural numbers. So now I'm going to say it's all the values that fall and include between 2 and 7, but I'm limited to the natural numbers. So x is this element of only the counting numbers or the natural numbers. And remember, this fatty n means natural numbers. So set builder notation can be more precise when I don't have an interval that's continuous to describe. So let's look again at one more. Let's look at E. And this time it's all multiples of 7. So we know for a fact, not multiples of 7. So we know for a fact this isn't continuous because we're talking about 7, 14, 21, and so on. So let's look. We're going to talk about x values such that x equals 7 times n. And so remember, this is the notation 7 times n. If n is 1, we're talking about 7. If n is 2, we're talking about 14. If n is 3, we're talking about 21. If n is 4, we're talking about 28, and so on. In fact, we're even talking backward. If n is negative 1, then we're talking about negative 7. If n is negative 2, we're talking about negative 14. So we're talking about a lot of values, but they're only multiples of 7. And we know that multiples of 7 are always on the integers. And so remember, a fatty z means integer. So we're not going to get any fractions or decimals. Multiples of 7 are always going to be integers. So we're looking at all x values in the integers, and we know that the set of integers is from negative infinity to positive infinity, and they're all the integers that are a multiple of 7. All right, so enough of that. Let's move on to functions. So describe whether the relation is a function. So remember, relations are tables that assign, say, an input and an output value from two different sets. So remember that if a relation is a function, then it has to pass the vertical line test. Right? So if I have a graph that looks like this, it's a function no matter how weird it looks, as long as for every single point that I can draw a vertical line, the input x on that line creates only one output. So an example of a graph that does not pass a vertical line test would be something like this, because at this vertical line, input x produces two outputs. So this is not a function. On a table, it looks like input, output. So if I have -3, -1, 0, 1, and 3, then I know I'm good to go, right? Because no matter what, I don't have two inputs. I don't have the same input listed twice. So no matter what, even if my outputs are all the same, so if the output is 0 for every single one of them, all that means is on a graph, 0, well, let's make them 1 so the graph is easier to see. 0 is just hard to show on the graph. No problem with 0, it's just hard for me to show it. So if all of the outputs are 1, that means we're talking about a horizontal line where if I put input 0, if my input x is 0, it points to 0 or 1. My input -3x points to 1. My input -2 points to 2. Points to 1. No matter what my input is, it only points to one place. That makes it a function. When identifying whether a relation is a function gets tricky is when you're dealing with an equation or a formula rather than a picture or a table. So let's look at a couple of those examples. Determine whether y is a function of x. So if x equals 3y squared. Well, in this case it's hard to tell, so let's solve for y because it's easy to tell once you solve for y. So I like my y on the other side, so I'm going to do 3y squared equals x. I'm going to divide both sides by 3. And then I'm going to take the, I'm going to take the square root of both sides. So don't forget the square root property. When you take the square root of both sides, you have to include the plus or minus, and so I get x over 3. So y equals plus or minus x over 3. Remember, that's a chicken feed situation where y equals the square root of x over 3 and y equals negative the square root of x over 3. So you can already tell that for the same input of x, you're going to get a negative value and you're going to get a positive value. So this is not a function because you get two different y's for the same x. Another example. B. So x squared plus y squared equals 9. So we already know this isn't a function because this is the definition of a circle with radius 3 and center at 0, 0. So the vertical line test on this is definitely not going to work. But we can find it out algebraically as well. We have y squared equals 9 minus x squared. Take the square root of both sides. So you get plus or minus. We're in the same boat we were in for problem A. 9 minus x squared. So this would factor and you'd get two different values. Or the plus and minus is going to give you two different values. So either way you look at it, this relation is not a function. So both of these are not functions. On the other hand, if I had y plus x squared equals 3, well, that's just y equals 3 minus x squared. That's just a parabola, and any way you graph a parabola, let's see, minus x squared is going to be downward facing, it's going to cross at 3, so it's going to look like this, but it's going to certainly pass the vertical line test.